So thanks a lot for the invitation. As I said, it's a great pleasure to be here. I would only be happier if I could be there physically, but hopefully soon. Feel free to interrupt whenever you want. So everything I'm going to talk about is joint work with George Moschidis, and that's not going to be exactly a colloquium style talk in the sense that it's actually going to contain proofs, but I believe it's accessible to experts, and really you should interrupt me at any time you want. All right, so let's just start. This is a talk about the Brunn-Minkowski inequality in Gauss space. So let's just start from the Brunn-Minkowski inequality in Rn, which is a very classical inequality about the volume about the Lebesgue measure in Rn. And it basically says that the volume function to the power 1 over n is concave. So what this means is that whenever you have two compact sets in Rn, A and B, and lambda in between 0 and 1, then the Lebesgue measure of lambda A plus 1 minus lambda B to the 1 over n is bounded below lambda times the volume of A to the 1 over n plus 1 minus lambda times the volume of B to the 1 over n. So the absolute value here is the Lebesgue measure, so the usual volume, and the Minkowski convex combination of sets in Rn is given by sort of the pointwise addition, right? So that lambda A plus 1 minus lambda B is the set of all lambda A plus 1 minus lambda B, where A is in A and B is in B. Okay, and we say a lot in this literature that this inequality captures the optimal concavity of the Lebesgue measure. And I'm going to explain what this means in a bit. But just bear in mind that it has a bunch of non-trivial equality cases. In particular, if A and B are homothetic convex sets, then this simply becomes an equality. You know, this is an extremely important inequality, and in convex geometry, but also beyond convex geometry. And just to give you an example, if you choose the set B to be a Euclidean ball of radius epsilon, and you let epsilon go to 0, then, oops, I'm sorry, then the two quantities will converge to the same thing, so you can divide by epsilon and see what you get. And what you get is exactly the isoperimetric inequality. So this means that among all measurable sets with a given Lebesgue measure, the Euclidean bonds have minimal surface area. So the isoperimetric inequality just simply follows formally from the Brunn-Minkowski inequality, but that's just one of the many reasons that this is important.
Alex, sorry, one quick question. Is the equality statement a characterization as well? Is that a if and only for, is there something?
Yeah, so if you, yes, I'm pretty sure it is. Of course, this is known. If you assume that the sets are compact, I think that's it. Because this holds true for general Borel sets, then you may need to be something.
Okay, yeah. Thanks.
Okay. So let's move on. This talk is about the Gaussian measure, but you know, there's sort of a general theory developing a lot in the 21st century, which is called Brunn-Minkowski theory. And modern Brunn-Minkowski theory tries to relate the size of the sum of given sets with the size of the individual summands. But the twist now from the classical Brunn-Minkowski inequality is that both size and sum are interpreted more loosely. So there's not simply, you know, Minkowski convex combination, Minkowski sum, and Lebesgue measure. And there are many questions of this nature, which most of them are actually wide open. But in this talk, we're going to have the following conventions. So I'm going to, by sum, I'm simply going to refer to the Minkowski addition. So this is not going to be different, even though in other parts of the theory it's very different. But the size of sets is going to be measured by their standard Gaussian measure. So the Gaussian measure of a set is the integral on the set of e to the minus Euclidean norm of x squared divided by 2 times the normalizing factor. So this just makes it the probability measure in the whole. Okay, so we want inequalities relating the Gaussian measure of the sum of sets in Rn with the Gaussian measure of the summands. Okay, that's the idea. And, you know, we're not the first to think about that. And there's actually a very classical and extremely important inequality from 1983, basically, which is the real, I would say, Brunn-Minkowski inequality in Gauss space, which is Ehrhardt's inequality. So this asserts the following. If you have any Borel sets A and B in Rn, then phi inverse of the Gaussian measure of lambda A plus 1 minus lambda B is bounded below by lambda phi inverse of the Gaussian measure of A plus 1 minus lambda phi inverse of the Gaussian measure of B. And now what is this function phi inverse? Phi is the inverse, the formal inverse of the distribution function of the Gaussian measure. So phi of x is the probability that a one-dimensional Gaussian random variable is smaller than x. And this is an increasing function, increasing and continuous and so on. And phi inverse is simply the inverse of that. Okay, so just again for comparison, in the Lebesgue case, we had that the Lebesgue measure raised to the power 1 over n is concave. Here we have that this function phi inverse of the Gaussian measure is concave on all Borel sets with respect to Minkowski addition. Now, let me just say that Ehrhard's proof required both sets to be convex. In fact, he devised a powerful tool which we call Gaussian symmetrization, and the Gaussian analog of Steiner symmetrization in the Lebesgue case to prove this. But sir, the general case that you just require the sets to be Borel is due to Borel with 2 L's from 2003, and he had a completely different proof which didn't go through Gaussian symmetrization. It went through a heat flow argument. Okay, and this is in fact a very important inequality. And just to give an example, it implies the Gaussian isoperimetric inequality, which says that among all measurable sets in Rn of fixed Gaussian measure, then the Gaussian surface area is minimized on half spaces. So sets in Rn for which, say, the first coordinate is smaller than s. And of course, because of rotational invariance, you can rotate the subspaces as long as they have the same measure, Gaussian measure. Okay. So that's Ehrhard. Now, similarly to Brunn-Minkowski, Ehrhard captures the optimal concavity of the Gaussian measure. And let me explain now exactly what this means and exactly what I'm going to mean by a sharp inequality in this talk. So let's suppose that you have some function, zeta n, so that zeta n of the Gaussian measure is concave, at least for sets which have probability different than 0 and 1. Okay, so just suppose that we have an inequality like that for some function zeta n. Notice that in the previous case, the function phi inverse does not depend on n, but in principle, you could maybe believe that as the dimension increases, you maybe get a better inequality or a worse inequality. So suppose that we have this function zeta n, and then plug a and b to be parallel half spaces. So for instance, capital A could be the set of x so that x1 is smaller than a, and b is the set of x so that x1 is smaller than b. Then let's just see what we have. So gamma n of a is phi of little a, gamma n of b is phi of little b, and then gamma n of the convex combination of the Minkowski convex combination is phi of the convex combination, lambda a plus 1 minus lambda b. So the inequality which we assume really says that zeta n composed with capital phi has to be a concave function. So in this sense, choosing zeta n to be phi inverse is extremum. You cannot get any more concave than that. Okay? So zeta n equals phi inverse is simply the extremal case. And this also emphasizes the fact that Ehrhard's inequality has a bunch of non-trivial equality cases, which are sets of this form. Now, in contrast to the Brunn-Minkowski inequality, the equality cases of Ehrhard were actually a big open problem that was resolved only a few years ago by Schoenfeld and Van Handel. At least when one is interested in Borel sets and not just convex. Okay. So are there any questions about Ehrhard, by the way? Okay. So now Ehrhard's a great inequality. Its main feature is that it simply does not see the geometry of the set. It's true for every Borel set. So it's basically a measure theory inequality. But that's in a way also its disadvantage. It's somehow oblivious to additional geometric properties of the sets. And in 2010, in a very nice paper, Gardner and Zvavitch undertook a systematic investigation of Gaussian inequalities in Brunn-Minkowski theory, and actually most of the results were in dual Brunn-Minkowski theory. So I'm not going to explain what this means, but basically the notion of summation changes here from Minkowski summation to something else. And perhaps the most influential part of their paper is an open problem that they posed at the end, which is the following. They asked, is it true that for every convex sets K and L in Rn, which contain the origin, and every lambda between 0 and 1, gamma n of lambda k plus 1 minus lambda l to the 1 over n is bounded below by lambda measure of k to the 1 over n plus 1 minus lambda measure of l to the 1 over n. So this means that, in fact, they ask, is it true that we have the same inequality as we have for the Lebesgue measure, simply for the Gaussian, under the assumption that the sets are convex and contain the origin? Okay. And it's very easy to see, and of course they noticed that you cannot hope to have this inequality for general Borel sets in R. Okay, and the way to see it is to take K to be just a cube in Rn, and L to be a point that's very, very far. Okay, and say lambda is equal to a half. Then the right-hand side in this inequality, the measure of L is just equal to 0, it's a point. The measure of K is a constant. But then on the left-hand side, you have the measure of a cube that's translated. So this is a cube in Rn that's centered at x over 2. Okay, so as you send x to infinity, the Gaussian measure at infinity goes to 0. So the measure of this cube will also go to 0. So this inequality simply cannot be true. You need a condition because the left-hand side goes to 0 and the right-hand side is simply a constant because of the gamma of k. So you need a condition that kind of says that, you know, the sets, both sets K and L, are around 0. Most of their mass is around 0 for the quantum. And the condition that they chose to ask was convex sets containing the origin. Now, very soon after, this was shown to be wrong. So in 2013, Nayar and Koch constructed an example showing that the answer is no, even for n equals 2. And their example was not something exotic. It was really just sort of two cones that were parallel to each other and they barely contained the origin. Okay, and the idea is that containing the origin, even under convexity, is not a strong enough condition to say that, well, actually, you know, most of the mass is concentrated there. But they asked a reformulation of the problem, which is whether the Brunn-Minkowski inequality in Gauss space with power 1 over n holds true if we assume the sets K and L to be origin symmetric. This means that a point belongs in K or in L, if and only if its antipodon belongs in K or in L. And this problem remained open for quite some time. And the main theorem that I'm going to explain to you today is that the answer is yes. So let me just mention that in comparison to what I was saying before, it was already observed by Gardner and Zvavitch that the dimensional Brunn-Minkowski inequality is neither a consequence of Ehrhardt's inequality, nor does it imply Ehrhardt's inequality for symmetric convex sets. So the two inequalities are kind of, you know, one beats the other in different regimes, and I'm going to come back to that in the end. So let's just see what's the idea here. There's a bigger phenomenon. Now, recall that the Gaussian measure is log concave. That's a classical fact. So the Gaussian measure of the Minkowski convex combination of two Borel sets is bounded below by the geometric mean of the measure of the sets. Okay. So the Gardner-Zvavitch problem is actually a strengthening of this inequality here, which is just log concavity for symmetric convex sets. Okay, so you can formally see that if you have the concavity with power 1 over n, then this of course implies log concavity, that just Jensen's inequality or something. So the idea here is that you have this inequality, which is measure theoretic, it holds true for every Borel sense, and you put a geometric assumption, which is symmetry and convexity, and you hope for a better inequality. And this is something that's been happening a lot in this theory, and the most famous example of the problem is the log Brunn-Minkowski conjecture. I'm not going to discuss log Brunn-Minkowski, but it's a very strong conjecture that in particular would imply the Gardner-Zvavitch problem and many other things. So in particular, if this conjecture were true, then we would have the dimensional Brunn-Minkowski inequality, this inequality here, for gamma n replaced by every symmetric log concave measure, and K and L being any symmetric convex sets. So this follows from a bunch of works, but there's a strong conjecture somehow behind this that we have no clue how to prove or whether it's true or not, or whether it's true or not. So let me just mention one example of a theorem of this sort that we know, and that's the important B inequality of Corderot, Fratelisi, and Morin. So it asserts the following thing: fix a symmetric convex set K, and look at the and two numbers A and B, and look at the Gaussian measure of the geometric mean of A and B, A to the lambda, B to the 1 minus lambda times K. So that's a scaling of K by the geometric mean of A and B. Then their theorem asserts that this is bounded below by the geometric mean of the measure of AK times the measure of BK with the correct exponents, of course. And now notice that if you plug in this inequality here, A and B to be multiples of K, then you get that just under the convexity assumption, the Gaussian measure of the arithmetic mean of AK and BK is bounded below by the geometric means of the Gaussian measures. And this is simply for convexity. This is, you just assume the convexity of K. But what they claim, their theorem, in fact, implies that that if you further assume that the set is symmetric, then you can improve the geometric mean, the arithmetic mean to a geometric mean. And that's obviously a stronger inequality because this is bounded below by that. All right, so this is just the prototype of a theorem where assuming the symmetry of your convex sets actually implies substantially stronger inequality. And this is quite important for applications. You know, there are small ball estimates, which we don't know how to prove without using this. This is something that has been used quite a lot. And that's not the only example. There are other instances of symmetry playing a role in Gaussian inequalities. Many of you may know the Gaussian correlation inequality. There's also the S inequality of Gardner and Zvavitch. So there are inequalities in the spirit. And the Brunn-Minkowski inequality should be viewed as one of those. Okay, so let me just tell you what was known. So the problem was posed around 10 years ago, but it had a lot of activity actually in the past 5 years. So first of all, Gardner and Zvavitch proved the conjecture. If K and L were coordinate boxes containing the origin, or if K and L were dialates, so multiples of a given symmetric convex set. And by the way, even for this case, that K and L are multiples of a given symmetric convex set, they needed to use the B inequality. So even in that case, it's not a trivial theorem. Then Kolesnikov, Livshyts, and Moschidis proved the inequality if K and L are small perturbations of a Euclidean ball. So they sort of proved it infinitesimally around the Euclidean ball by using the spherical Poincare inequality. Then Livshyts, Moschidis, Gardner and Zvavitch proved it if K and L are ideals. Now, I'm not going to define ideals exactly, but a special case of that is if K and L are what we call unconditional convex sets. So this means that you have sets K and L in Rn, which are symmetric under reflection with respect to the n coordinate hyperplanes. So of course, that's a much stronger symmetry assumption that means symmetric around the origin. Then Brunn and Nicholas relaxed this a little bit by proving it for K and L, which are weakly and conditional. And there's a different direction, which is for n equals 2. So for the plane, the inequality is known by combining results of Borodsky, Ludwig-Jan, Seroglu, and Livshyts, Moschidis, Gardner and Zvavitch. And finally, there was a theorem earlier this year by Borodsky and Kalantzopoulos who proved that if K and L have n hyperplane symmetries. Now, the difference between this and unconditional sets is that the hyperplanes do not have to be the coordinate hyperplanes, and they don't have to be orthogonal. Okay, so you see there was quite a lot of attention, and there are also several other papers which extend these results over here to different measures different than the Gaussian, because as I said, the log Brunn-Minkowski conjecture predicts it for arbitrary symmetric log continuum measures. Now, in my opinion, the first real sort of breakthrough towards the problem was in 2018, where Kolesnikov and Livshyts took a different route to attack the problem. And this was inspired by very important earlier work of Kolesnikov and Emanuel Milman. And the main idea is to prove the dimensional Brunn-Minkowski inequality infinitesimally. So you really assume that K and L are small perturbations of each other, see what happens, and then there's sort of a local to global principle saying that this infinitesimal in fact implies the global. Now, I want to go on and explain the formulation. This is a good point. I could ask for questions, concerns.
So I have one, which is on. So the extension, you say the Brunn-Minkowski should hold for any symmetric log concave measure. Is that correct? Is it known? And
Yes.
and also, but this variant for the Gaussian instead of for log concave, is it the dimensional version, or is there another function?
Yeah, right. No, I'm talking about the dimensional. So the conjecture is that the dimensional, the 1 over n power, holds true for every symmetric log concave measure.
Okay.
And it's really unclear if there's an Ehrhard-type extension to other measures.
Okay.
Ehrhard's quite unique for the Gaussian as far as.
Okay. Thank you.
Yep. So I'm going to need a little bit of notation. So now recall that the generator of the Ornstein-Uhlenbeck semigroup is the elliptic differential operator on Rn, who acts on a smooth function in the following way. So L of u of x is the standard Laplacian of x minus some xi diu of x. So that's the Laplacian minus x dot the gradient of u. Okay, and this really serves the role of the Laplacian in Rn equivalent to the Gaussian measure, in the sense that it satisfies an integration by parts formula. So the integral of Lu times v, the Gaussian measure on Rn, is minus the integral nabla u dot product nabla v, the Gaussian measure on Rn. So it satisfies the integration by parts formula, which in the case of the Lebesgue measure you would have for the Laplacian. And also I'm going to denote by A sub HS the Hilbert-Schmidt norm of a matrix. So the Hilbert-Schmidt norm is just the square root of the sum of all the entries of the matrix squared, just the Euclidean norm. And now here's the local to global principle, which again is due to Kolesnikov and Livshyts and builds upon work of Kolesnikov and Milman. So fix a number delta between 0 and 1. And suppose that for every symmetric convex set, every smooth symmetric function u on the convex set, which solves the elliptic equation Lu is equal to 1, satisfies this functional inequality. Okay, so the functional inequality says that if you integrate the Hessian of u squared plus the gradient of u squared with respect to the Gaussian measure, and divide by the Gaussian measure of k, so what you have on the left-hand side is a probability measure, then suppose that it's bound below by delta over n. Okay? Then you have the dimensional Brunn-Minkowski inequality with exponent instead of 1 over n delta over n for every symmetric convex set. Okay, so the local version here is a functional inequality. So you have this functional of the function u. It's a functional inequality for solutions of a given elliptic equation in your convex set. So the result was that this statement, this functional inequality, implies this thing. And then the main sort of geometric result is that if you have a set which simply contains the origin and u is any smooth function solving the equation, so you completely forget the symmetry assumption, you have fewer assumptions, then the function on which you had this f of u over here is bounded above by 1 over 2 times n. And this in fact implies the Gaussian Brunn-Minkowski inequality with exponent 1 over 2 times n for convex sets simply containing the origin. So you see there's a more relaxed assumption, which is not central symmetry and that you just contain the origin, but in fact you get, because of that, you get a weaker inequality. Instead of getting 1 over n, you get 1 over 2 times n. And we know by the result of Nayar and Koch that for this class of sets, you simply cannot go all the way up to 1 over n. And by the way, the constants are not matching. We know that it's 1 over 2 times n, but it cannot be, I don't know, 0.7 over n, something like that. So our main result is really completing the program of Kolesnikov and Livshyts. So for every n and every symmetric convex set, every smooth symmetric function solving the elliptic equation satisfies the functional inequality with lower bound 1 over n. So the average of the Hessian squared plus the gradient squared is bound below by 1 over n. So it's really completing the program. And the plan for the rest of the talk is that I'm going to first show you the proof of the local to global principle. So explain why the functional inequality implies the geometric inequality. and then show you the proof of the local inequality. And towards the end, if there's time, I'm going to discuss an open problem. So I'm going to need to remind you, is there any question about the statement? Okay. So I'm going to remind you a little bit of terminology from convex geometry, which is that of a support function. So if K is a symmetric convex set, then the support function of K, denoted by H sub K, is a function on the sphere, and H sub K of a direction is the supremum over all x and K of x dot theta. So what you do is that you have your symmetric convex set, you project it on the line that's in the direction of theta, and you measure the length of this interval, joining 0 and that point. And you can check that if K and L are symmetric convex sets, then the support function of a linear combination with positive coefficients is simply the linear combination of the support functions. Okay. So the local to global principle. So I'm going to convince you that functional implies geometry. This has very little to do with the Gaussian measure. So in fact, I'm going to do it for any log concave measure. So take a measure mu, which has density e to the minus v. So v is now a convex function. So e to the minus v is log concave. And fix two symmetric, smooth, strictly convex sets K and L. Now, you want to prove the functional inequality, you can assume that your sets are as nice as you want. And denote by K sub lambda the convex combination 1 minus lambda times K plus lambda times L. And what you want to prove is that the function, which is the measure of this set K lambda to the power delta over n, is a concave function. That's really just the statement of the dimensional Brunn-Minkowski. So you want to prove that this is concave, and what can you do? You can differentiate in lambda, and differentiating in lambda gives you this condition over here. So the second derivative of m times m is bound above by n minus delta over n times the first derivative squared. Now, if delta is equal to 0 here, what you have is really log concavity, and that's somehow the well-known condition for log concavity. And the simple observation is that because of homogeneity, it suffices to take lambda equals 0 here. Because really, what's the picture above? You want to prove that the function is concave. So you take any K, any L, and any lambda in between. So this says that, in the space of convex sets, you take any line segment joining K and L. But because and the statement below really says that for any line segment, you can just look at the leftmost endpoint. But if you have a point in between, you can just take the subinterval that this is its leftmost endpoint, and that's it. So that's a sort of a triviality that this inequality is something that you can just check for lambda equals 0, because you can just change the parametrization if you want to prove it for an intermediate lambda. And now let me just notice that you can view this, since we're talking about lambda being very close to 0, we want to compare derivatives, we can view K lambda as a perturbation of K, because it's 1 minus something small times K plus something small times L. And in fact, this can be expressed very nicely at the level of support functions. So the support function of K lambda is a support function of K plus lambda times this function psi, which is the difference of the support functions. So what you do really is that you take K and you infinitesimally push it in the direction of this function psi. That's how K lambda perturbs K. And now, okay, let's just go back here. We want to prove this inequality with the first and the second derivatives. So the first thing we have to do is compute the first and second derivatives. And that's actually doable. So for the case of the Lebesgue measure, that's actually kind of classical, but for the general case, it's due to Kolesnikov and Milman. And these are identities. So let's just go and see what happens. So for x in the boundary of K, I'm going to denote by n sub x the unit normal of the boundary, because we have assumed that the set is strictly convex, so that's fine. And I'm going to define the function f on the boundary to be f of x is the function psi, which was defined on the sphere. It's the difference of support functions at the unit normal. Then it's not very hard to see that the derivative at 0 is the integral on the boundary of this function f with respect to the restriction of mu on the boundary. Okay, so what's happening here is that we have our set K, we are pushing it in the direction of psi, and you want to check the infinitesimal difference, right? So what you have is indeed that you measure psi because that's really what f is, on the boundary with respect to this measure. So this, in fact, is not very hard to prove. Now, the second derivative is actually more complicated, and for this talk, it's not really going to matter what it is exactly, but what's going to matter is somehow qualitatively what it contains. So let's see. It's an integral again on the boundary with respect to this restricted measure. Now, the first term here is the weighted mean curvature of the boundary of K, which is a surface in Rn at the point X. And weighted here refers to the fact that it's the usual mean curvature minus a term which takes into account the measure. Now, V is the potential of the measure. Here you have the second fundamental form to the power minus 1. And here you have the derivatives of the function f. Okay, so anyway, it doesn't really matter what this is. I'm not going to use it. But you should bear in mind that somehow qualitatively it measures it depends on the geometry of the boundary of K, on the derivatives of the function f, and the measure that you had, and the gradient here, the potential of the measure. Okay, so that's an identity. And now I can just rewrite this inequality with the first and second derivative using this. So what I have to show is that the integral of the boundary of this quantity, which I'm simply going to defer from, I'm simply going to refer to from now on as phi. So phi, depending on the boundary, v, f, and the gradient, is bound above by n minus delta times n times the measure of K, times the integral on the boundary of f with respect, that's not the gamma here, that's mu, d mu on the boundary. Okay, so that's, in principle, that's sort of a Poincaré type inequality on the boundary of the convex set K with respect to this measure mu. And we'll just say that when delta equals 1 and mu is the Lebesgue measure, this first appeared in work of Kolesnikov, who actually said, we know the Brunn-Minkowski inequality, we're going to differentiate it in this way, and he proved this inequality this way. Okay, so this is what we have to prove. The integral of this mysterious function phi is bounded above by this fairly simple quantity. And now here is, I think, the main idea in this local to global principle. So we're going to denote by L sub mu the elliptic operator that's associated to mu. So it's the Laplacian minus the gradient of the potential, comma, the gradient of u. Recall that before this was the potential for the Gaussian measure is x squared over 2. So its gradient is just x. So that's really the extension, the measure, the operator which satisfies the integration by parts formula with respect to mu. And then we have a theorem that's called the Riley formula, which tells you that if you have any convex set and any smooth function on K, then you can do integration by parts with respect to this operator L mu. Sorry, there's a typo here on K. So the integral of L mu of u squared is the integral of the Hessian squared plus this quadratic form of the gradient of u. So the Hessian of v nabla u, plus boundary terms, which depend again on the measure, the surface, the potential, u, and its derivatives. And again, I'm not going to tell you what the boundary terms are, but let me just say, for those of you who are familiar with this, if K is the whole Rn, so if there is no surface, then the integral on Rn of this is the integral on Rn of this, and this is what's called the gamma 2 functional. So that's a very well-studied quantity. The twist is that when you have sets which are not Rn, you have also some boundary terms. Okay, and here is the magical somehow observation, which is due to Kolesnikov phenomenon. So we have this function psi, which depends on a function defined on the interior of K. And before we have this function, we had this function phi, which depended on the function on the boundary. So if this function f on the boundary is the Neumann boundary data of u, so f is the perpendicular derivative of u on the boundary, so it's the dot product of the unit normal with the gradient, then phi at f is bounded above by psi at u. Okay, and let me just say that here I'm not hiding from you some kind of deep inequality. Okay, so this inequality is just AMGM but there's no chance I can prove it for you because I've not told you what psi is, and I've barely told you what phi is. But let me just say that the ideas here lie in the identities, in the Riley formula, and in the computation here of what phi is. Okay, so I'm not hiding from you any deep inequality. And now let's just take a step back and remember where we were. So we wanted to bound phi from above, but phi is bounded by psi. So it suffices to bound psi from above. And the integral of psi on the boundary can be expressed as an integral on the interior. So let me phrase it, but I want to be really careful about the quantifiers. So remember that we had to show that for every symmetric K and for every symmetric F, phi was bounded above by this. Okay. Now we know that this inequality holds true for every U which has Neumann boundary data F. This means that we have the freedom given F to choose the correct U. So what we figured out is that it suffices to show that for every K and for every F, there exists a U with Neumann boundary data F, so that this quantity here, which is simply the integral of psi by the Riley formula, is bounded above by the right-hand side we had before. Is this clear? Are there questions? Okay, and now we're very close to the local. So you see, this doesn't look very good so far, but we are getting close to the local to global principle because this term appears. Now, here's the last observation. Now, if the integral of f on the boundary is equal to 0, then the inequality is true, because remember what we want to do here is that we want to improve this delta from 0, which is log concavity, to 1. All right, but if this integral vanishes, then this quantity here, is just 0. So this follows from log concavity. So we can assume that it's non-zero, and in this case we can actually rescale so that the integral of f is equal to the measure of k. The integral of f on the boundary is equal to the measure of k. In this case, the equation Lu is equal to 1 has a unique solution with Neumann boundary data f. In fact, the constraint for this solution, for this equation to have a solution, is exactly that the integral of f on the boundary is equal to the integral of Lu on the interior, which is just the measure of k. Okay, so then, we said that for every f there exists a u. Now the u which I'm going to choose is the unique u which solves the equation Lu is equal to 1 with boundary Neumann data f. Okay, and if you just go to this inequality, plug in Lu is equal to 1 and the integral of f is equal to the measure of k, and rearrange the terms, you get exactly this quantity. So 1 over the measure of k times the integral of k of this quantity, which is the gamma 2 functional, so the Hessian squared plus Hessian of v nabla u d mu on k is bounded below by delta over f. And that's the proof of the local to global principle. Okay, so it's really differentiating and choosing the right function u. Now, notice though that even though up until this point we were completely equivalent, because what we did was just, want to prove a function was concave, we just differentiated. At some point we lost something. So here we use this one inequality that phi is bound above by psi. And this means that, there's a chance that our local to global principle in fact asks for something very strong. So it's a reasonable sanity check to ask, well, can we actually prove the Lebesgue-Brunn-Minkowski inequality via this technique? Okay, so the formulation is the following: just applying what I just said for the log concave measure to be the Lebesgue measure. So for every k and every u, every symmetric k and every symmetric u, of course, with delta u is equal to 1, we want to prove that 1 over the volume of k times the integral of k of the Hessian squared. Now the potential is just 0, so there is no other term, is bounded below by 1 over n. Okay, so if we have any hope to do it for any log concave measure, we should at the very least do it for Lebesgue. And this inequality is actually true. And here is the very simple proof. Now, the Hessian of U squared, the Hilbert-Schmidt norm of the Hessian squared, is simply the sum of the eigenvalues of the Hessian squared. Okay, that's just what the Hilbert-Schmidt norm is. And now you can use Cauchy-Schwarz and bound this below by 1 over n times the sum of the eigenvalues with a square outside. But the sum of the eigenvalues is just the trace of the Hessian squared divided by n. And the trace of the Hessian is just the Laplacian divided by n. Okay, and we just assume that the Laplacian is equal to 1. Okay. So in fact, in this case, the measure does not play any role. It's not about the integral, it's about the integrand is bounded below by 1 over n. Okay. So this is, by the way, you just saw a complete proof, or almost complete, because I hid some identities from you, of the Brunn-Minkowski inequality on Rn with the Lebesgue measure. But we don't want to do it for the Lebesgue measure, we want to do it for the Gaussian, and in principle for other measures as well. So let's just see what Kolesnikov and Livshyts did to get the 1 over 2n bound. Okay, now we have K symmetric and U symmetric, and U solves the equation Lu, which is the Laplacian minus x dot nabla is equal to 1. Okay, and I'm going to denote by gamma sub k the Gaussian measure restricted on the convex set k. So it's the Gaussian measure of the intersection divided by the Gaussian measure of k. Okay, so the quantity that I'm interested in is the integral d gamma k of the Hessian squared plus the gradient squared. Okay, so what they do is that they apply exactly the same inequality. So what we used before for the Lebesgue measure is that the Hessian squared is bounded by the Laplacian squared divided by n, and they do exactly the same. But now the twist is that the Laplacian is not equal to 1 anymore. It's equal because of the equation, because we've changed the equation for the Gaussian case. It's equal to 1 plus x dot nabla u at x. Okay, so that's what you get simply from Cauchy-Schwarz. Now notice that this is a quantity which depends just on the gradient of u. So you can bound it from below. So if you denote by capital V to be the gradient of u at the point x, then for a fixed x, the minimum of this quantity, as you can check by whatever, Lagrange multipliers or something, is 1 over x squared plus n. So by combining the two, the integral that we wanted to bound from below is bounded below by the integral of 1 over x squared plus n d gamma k. And so far, everything is pointwise. Okay, again, there's no, the measure didn't really play any role. Well, it played in the equation, but I mean, we didn't really integrate so far. Okay, and now you have this integral of 1 over x squared plus n d gamma k. And it's actually not very hard to show that if k is star-shaped, then the k which minimizes this is actually Rn. So the minimal value that you can have for this is the integral on Rn, and then this is something which you can evaluate, and that's 1 over 2n plus a constant over n to the 3/2. So that's how you get the 1 over 2n bound. There are two pointwise inequalities, and this bound here, which is actually simple, it holds for every star shape. And that's how you get Gaussian Brunn-Minkowski just with exponent 1 over 2n. And you can notice that indeed all we used was that the set was star-shaped, and okay, there's convexity in the previous argument, the local global, but we didn't use central symmetry in this argument. So, you know, the natural thing to say is that now we have these 3 steps. You concatenate 3 steps, you get the inequality, and you can ask, where did we lose, right? So in the last step, we clearly didn't lose because there's an equality case, k is equal to Rn. And then you look at step 2 over here. And you can ask for which V is this becoming an equality, okay? And that's something which you can actually evaluate very easily. And it just so happens that the vector V, which attains equality, is the gradient of a given function. Okay, because V was the gradient of U. And it's the gradient of this function U0 minus 1/2 log x squared plus n. And remember that our function U was supposed to satisfy this constraint. But unfortunately, this function U0 does not satisfy the constraint. So you can go back and say, well, maybe, you know, maybe since the fact that I forgot the constraint after step 1 was too crude. And maybe, you know, if I take it into account somehow in step 2 here, I have some hope to improve. But unfortunately, that's simply not the case. And that's one of the first things we realized in this project, that you can actually cook up a convex set K, which is really, it's not something sophisticated, it's a narrow cylinder, and a symmetric function which solves the equation on K, so that this quantity, which is exactly the quantity that we ended up with after step 1, okay, after just the Cauchy-Schwarz inequality here, is really 1 over 2n plus ln log 1. Okay, so the fact that we lost has nothing to do with the fact that we forgot the constraint. And this at first sounds like bad news, but in a way it's good news, because it means that you know what the enemy is. And the enemy is exactly this inequality here. Is exactly the inequality that you start from, okay? So this is too crude, and we need to find something more sophisticated. So let me remind you, we prove this inequality for symmetric complex sets and symmetric functions. So let me just show you how we do that. Are there any questions so far? No one has spoken for a while, so I hope you can still see me here. So we want to prove this inequality for symmetric convex set and symmetric functions. So we need a little bit of notation. If you have a matrix A, I'm going to denote by A hat its traceless part. So it's A minus the trace of A divided by n times the identity matrix. Okay. And you know the identity matrix divided by square root of n is a unit vector on the space of matrices with the Hilbert-Schmidt norm. So this quantity here is the multiple, is the projection effectively of A on the line which is generated by the identity matrix, and A hat is the projection on the orthogonal complement. So in particular, you have Pythagoras' theorem that the Hilbert-Schmidt norm of A squared is the Hilbert-Schmidt norm of A hat squared plus the trace of A squared divided by n. Okay, they're just basically linear algebra, it's nothing sophisticated. And in particular, if you apply this to the Hessian, you have the traceless part of the Hessian, and then you get that the Hilbert-Schmidt norm of the Hessian squared is the same as the Hilbert-Schmidt norm of the traceless part squared plus the Laplacian squared divided by n. Okay, so remember that before, the thing which we shouldn't do was to bound the left-hand side from the second term here. Okay, and this is exactly what we didn't do now, because we're really keeping track of the deficit. Now the question is, what does this deficit measure? So what it measures is the distance of u from the kernel, of this operator nabla hat squared. So it measures in a way the distance of u from the space of all functions, the traceless part of whose Hessian is equal to 0. In other words, the distance of u from the space of functions whose Hessian is a multiple of the identity matrix. Okay, so since you can write this identity for every r which belongs in the kernel, you can in particular write it for this function, which is x squared divided by 2n, since the Hessian of this matrix is the identity divided by n. And notice that also the Laplacian of this is equal to 1. Okay, so now let me rewrite the right-hand side here by the previous identity, by the identity expressing the traceless part with respect to the full Hessian. So the traceless part of u minus r squared is the Hessian of u minus r squared minus the Laplacian squared divided by n. And the Laplacian of r is equal to 1, so that's minus delta u minus 1 squared divided by n. Okay, so far I've done nothing. Okay, but now these are a few identities which we can actually combine. So we wrote the Hessian of u squared like this, then we wrote this as the traceless part of u minus r, and the traceless part of u minus r can be written as the full Hessian of u minus r. So if you put everything together and open up the squares here, what you get is that the Hessian of u squared is the Hessian of u minus r squared plus 2 over n times the Laplacian minus 1 over n. That's simply what the identities give, and that's a triviality. I'm just explaining to you where it comes from. And now is the time to remember that u solves the equation. So L of u is equal to 1, which means that delta u is 1 plus x dot nabla u. So you substitute delta of u and you get this quantity here. and so for everything is an identity. Okay, but this means that we are in kind of a good shape. And the reason we're in a good shape is that, we have the 1 over n here that we wanted. Remember, we want to bound the integral of this by 1 over n. This first term over here is a second order, very, very positive term. And in the middle, we have a first order term. So in principle, what we have to do to finish is to say that the second order term can be bounded below by the absolute value of this first order term, or at least by minus this first order. Okay. And here comes the only non-trivial tool in the proof, which is the Brascamp-Lieb inequality. So recall that the Gaussian measure on K can be approximated by smooth measures, log concave, whose Hessian is bounded below by the identity matrix in the PSD sense, in the positive semi-definite sense. Okay, that's just very simple. It's your measure in fact has potential 1 on the interior, and then there's a cutoff which takes it to infinity. So you just need to do an approximation there, and that's true. So Brascamp and Lieb in '76 proved a very important inequality, which is basically the Poincare inequality for measures satisfying this potential lower bound. So if the Hessian of the potential is bound below by beta times the identity, and you have this measure e to the minus v of x dx, then the variance of the measure, which is the integral of the function squared minus the square of the integral of the function with respect to this measure, is bound above by 1 over the constant, 1 over beta, times the integral of the gradient d mu squared. The integral of the gradient squared d mu. So in particular, since everything here is just, since these are just integrals, we have the same property for the measure gamma k, since it can be approximated by such measures in a weak sense. Okay, so we have this Poincare inequality at our disposal, so let's apply it. We are going to apply it to the function which is the ith derivative of u minus r. Okay, remember we want to bound from below the Hessian of u minus r. So applying the Poincare inequality to the ith derivative of u minus r, we need to notice that u is even and r is even, so the ith derivative is odd, and k is a symmetric convex set. So this means that the variance is simply the integral of the function squared, because of the integral on k is just equal to 0. You're integrating an odd function in a symmetric set. So the variance, which is the integral of the function squared, is bound above by the gradient of di, and the gradient of di is just the sum over j di dj. Okay, and then you're just going to sum up this quantity in I, goes from 1 to n. So what you get is on the left hand side the sum over I and j, which is the Hessian squared of u minus r, is bounded below by the gradient of u minus r. And now the gradient of r is just x divided by n. Okay, r is just a very simple function. So you can, right here, you can just expand the square. So this is the gradient of u squared minus 2 over n times sum xi diu plus x squared divided by n squared. Okay, and this is exactly the cross term that we had before. So remember that we wanted to show that the Hessian squared plus exactly this term is bounded below by something positive. And now putting everything together, we have additional positive terms. One is coming from here, one is right here, and there was this gradient in the beginning that we also had. So at the end, this is bound below by something positive plus 1 over n. And that's just the end of the proof. But you see that there was a significantly stronger use of the symmetry assumption here that was not available in the previous proofs that were mainly pointwise bounds. Here you actually needed to do something, use somehow the symmetry in a more essential way. So that's a good point for questions. I have 2 more slides. Do I have time for the 2 slides? Or?
Yeah, if you want to, I mean, there's still 3 or 4 minutes if you just want to take it.
Yeah, sure. Okay. Okay. So that's the end of the proof. Let me just say a quick word. So, when we proved this inequality, a bunch of people told us that it actually looks too strong in a way, because you want to get a bound of 1 over n and you have these additional positive terms. So what these positive terms do for you is that they actually prove a stronger inequality. So you can find the function sigma n, so that the function sigma n to the minus 1 raised to the 1 over n -1 is the inverse here, is strictly increasing and strictly concave, so that sigma n of the Gaussian measure is a concave function with respect to Minkowski addition. So this is a genuinely stronger fact from the dimensional Brunn-Minkowski inequality, and the way you get it is that you just repeat effectively the previous proof, but take into account this x squared over n squared as well. But what this says is that in fact the inequality which we proved, the dimensional Brunn-Minkowski inequality, in fact has only trivial equality cases. Okay, because the way to prove now the dimensional Brunn-Minkowski inequality is to get this inequality, which is stronger, combined with the strict concavity of this function. Okay, so if you have an equality here, then you also have an equality in the strict concavity, which means that the measure of K is the measure of L is the measure of the complex combination. And this is something, so this means that you have equality in, Prekow-Leindler or Ehrhard and so on, and we know that this can only happen for K is equal to L. So we have trivial equality cases in this inequality, which remember was not the case for Ehrhard and was not the case for Brunn-Minkowski. And the right question is, what does this mean? And in my opinion, this means that we have this wrong inequality. So I want to close with an open question, which I think is very tantalizing. So does there exist an optimal increasing function psi n such that psi n of the Gaussian measure is concave over all symmetric complex sets? Now the real question is, what does optimality mean here? So here's two properties that I would like this function psi n to have. First, I would like this inequality to be stronger than both Ehrhard and dimensional Brunn-Minkowski. So I think that's something which is desired from this. We have now two incompatible inequalities, and it's clear that there exists a joint strengthening, and we don't know what this is. But I think that the way to test optimality is for this at least to have some non-trivial equality cases. And there are very few things which I know about this question. And one thing though is that the equality cases cannot be too trivial. So in particular, you could think of the following situation: you can take this function psi n, capital Xi, to be at R to be gamma n of R times K, and you could ask, is it true that the little psi n to be equal to capital Xi n inverse satisfies this inequality? Now, if this were true, the inequality would be an equality for all multiples of the given convex set K. Okay, and what we know is that this cannot happen. So the function psi n cannot be that simple. So the equality cases cannot be this one parameter family. So it's clear that there exists some kind of phase transitions. And in fact, this brings a lot to mind the phase transitions in the conjectured Gaussian isoperimetric inequality for symmetric complex sets, which is a well-known problem. Ideally, this conjectured inequality would also imply isoperimetry for symmetric complex sets, but who knows? But you see now, these are very, since it has to imply in principle, if it exists, all those things, then it would have to somehow bring together very different kinds of proofs, because Ehrhard is something that you prove via Gaussian symmetrization or the heat flow. Then for the dimensional inequality, we have this local to global technique, which is very different. And finally, for Gaussian isoperimetry, the current methods that have given partial results are via Kolesnikov mean curvature flow, Gaussian mean curvature flow, so that are due to Heidelman, by the way. So in principle, to prove an inequality that looks so strong, I think you have to come up with very interesting maths. So I think that's a very tantalizing open probe. And yeah, I think that's a good point. I'll stop here.
Okay, thanks a lot, Alex. Let me first ask participants all to unmute and give a round of applause to Alex, and then we can have some questions. So everybody should be able to unmute. Okay. Any questions? Yes, Suri.
I have a small question. It's a sort of general question. I believe the classical Brunn-Minkowski inequality was used by someone to study something called shapes of worn stones in the 70s. It's about stones on a beach which are pounded by waves, and they ultimately tend to attain a spherical shape. Perhaps it's like isoperimetric, I don't know. But So the Gaussian measure also, is there some such thing? But
I don't know what this is, but
Okay.
but in principle, you know, you could depends on what kind of geometry it requires. Like if it's just something about Brascamp, maybe Ehrhard already, which is known, could give something interesting. But yeah, I'm afraid I'm not. I don't know what this is. But if you have, to look into.
It is just, I saw this paper in the 1970s by somebody in Fire. It's called Shapes of Worn Stones, and this applies the Brunn-Minkowski classical one.
I see. Okay.
Thank you. It's a very nice talk. I don't have.
Any other questions? Okay. So I had one, was that the functional form of the inequality you had. So the suggestion was that because, you know, the way you set up the Laplacian, it was a generator whose stationary distribution was the Gaussian, and then you took one whose stationary is the Lebesgue for the classical Brunn-Minkowski. And in general, for any log concave, you have such a L. You can come up with a Laplacian like this, right?
Exactly. It's this L mu, which I didn't know. Let me just find it for people to see. Exactly, it's right here.
And in general, this local to global principle is in this generality. Is that correct? That, or, I mean, do you expect it for more than log concave? No. Or
so okay, if I'm not mistaken, in the inequality which I claimed is trivial, so this phi being bounded above by psi, I think that you use that the Hessian is a positive definite matrix, and that's probably how you apply AMGN.
okay.
So I would know where to start with more general. So this would okay. Let's see. So far in the previous step over here, I think that so far we're not using much, and when we just differentiate it, I think one has to check that too. But over here, at least when one wants to use the Rayleigh formula, which is the main idea of Kolesnikov and Milman for this problem, and also for the logarithmic Brunn-Minkowski problem, then I think that log concavity just becomes essential.
Okay. Can you go one slide before? I had a small technical point thing. Isn't the mu of k to the power delta by n? I thought somehow there should be there was a power delta by n for m of 0, right?
No, because you see, when you differentiate the function, the exponent just sort of comes out, it becomes additive. So you have the measure to the power delta over n, and you evaluate the derivatives.
Okay.
Zero. So delta appears right here, so it becomes a deficit.
Okay. Okay. No, but m of 0, m of 0, isn't it mu of k to the power delta by n, right? Your definition.
Okay. Now I see. What's happening?
So I was thinking the mu of k, is it by m of 0, or so I was wondering for that.
You're right. Okay, there's a typo somewhere. So this has to be. Yeah, this is a typo somewhere. You know, maybe there are normalizing constants here. Or maybe. Yeah, I think there are normalizing constants in m prime and m double prime that are going to make things vanish. I think that's
okay.
So in principle, this shouldn't. There should just be a deficit of power 1. But yeah.
Okay. Yeah. Okay. Thanks. No problem. Yeah. Okay. I was wondering if it was missed. Yeah. Okay, thanks. Any more questions or comments if anybody has? Maybe we can, maybe a few more minutes.